Hi everyone, and welcome to week 5 of the Introduction to Causal Inference course. In this lecture, we'll be focusing on identification. Last week, we saw the most common example of identification, which is the backdoor criterion, which allows us to identify causal effects via the backdoor adjustment. But that's not the only way to identify causal effects. You don't have to satisfy the backdoor criterion to identify causal effects. As always, leave any comments or questions in the YouTube comments down below as they come up during the video. Here is the outline of this lecture. Before we get to more general identification, we're going to revisit randomized experiments and explain why they're so magical, why randomized experiments make causal inference easy. Then we'll cover the Frontdoor Adjustment, which is another easy graphical adjustment like the backdoor adjustment, but it's still not the only way to identify causal effects. So then we move to Pearl's do calculus. This is like a calculus of identification. We'll see that whenever we can identify a causal effect, we'll be able to do it using the rules of do calculus. And the rules of do calculus operate on mathematical expressions. Given some causal quantity and a causal graph, the rules of do calculus don't immediately tell us whether or not that quantity is identifiable from just looking at the graph, like the backdoor criterion does. So in the last part of the lecture, we'll see how we can know when some quantities are identifiable by just looking at the causal graph. With that, let's get into why randomized experiments are so special. This is the main message to take away from this part of the lecture. Randomized experiments are magic. For context, recall that there's no way to know if we have unconfoundedness or if we have satisfied the backdoor criterion. And that's because there always could be some unobserved confounders. This is a problem we'll always have to deal with in observational studies when we only have observational data. But randomized experiments are different. Randomized experiments are magic because they make it so that we have no unobserved confounding. Another way of saying this is that we have unconfoundedness, or we know that the backdoor criterion is satisfied. First, we'll quickly recall randomized experiments, or randomized controlled trials in this case. In a randomized controlled trial, we would flip a coin to determine whether an individual goes to the treatment group or the control group. So the only variable that influences treatment is the outcome of a coin toss, or some random number. Recall our example of people going to sleep with shoes on and waking up with headaches. So we want to measure the effect of going to sleep with shoes on waking up with a headache. And in this example, it turns out that a lot of the people who went to sleep with shoes on went to sleep drunk. And a lot of the people who went to sleep without shoes on went to sleep sober. So drinking the night before is a confounder in this example. And then recall how we imagined we might turn this into a randomized control trial. We could go into the rooms of all the people who slept with shoes on and flip a coin to decide whether to leave their shoes on or to take them off. And then similarly with the people who went to sleep without shoes on, we would go into their room, flip a coin, and decide whether or not to put shoes on them or leave their shoes off. That would change these groups from the people who went to sleep with shoes on and the people who went to sleep without shoes on to the people who slept with shoes on, because, we decided who slept with shoes on, and the people who slept without shoes on. And now that we've turned it into a randomized control trial, because we've used a fair coin to determine which group each person ends up in, to determine whether they sleep with shoes on or off, now the groups end up being comparable. We end up with the same number of drunk people in both groups, and similarly we end up with the same number of sober people in both groups. Alright, so that was just recalling randomized experiments and the specific example that we'll use. And now we're going to go into a few different perspectives on why randomized experiments are special. If any one of these perspectives clicks with you, then that's great. I give a few just to make sure that you understand why randomized experiments are magic, and some of them will be more intuitive than others. The first is comparability, or covariate balance, And that is that the treatment and control groups are the same in all aspects except treatment. So, I mean the distributions of all of their covariates are the same. In the example with drinking, shoe sleeping, and waking up with a headache, the main covariate that you want to have the same in both groups is drinking, because it's a confounder. But because it's a confounder, you end up with very different distribution of drinking across the two treatment groups. Most of the people who go to sleep drunk end up going to sleep with their shoes on, and most of the people who go to sleep sober end up going to sleep without their shoes on. But as we just saw, if we determine which treatment group each individual is in by a fair coin, then the distribution of drunkenness ends up being the same in the two treatment groups. So the intuition is that because these two treatment groups are the same in all relevant aspects except treatment, the difference in observed outcomes between these two groups must be due to the treatment. Right, so if we have covariate balance, then association is causation. What we're now going to do is make this more clear by first showing that randomization implies covariate balance, and then showing that covariate balance implies that association is causation. We'll start with just defining covariate balance more formally. We have covariate balance if the distribution of covariates X is the same across treatment groups. In math, we write this as follows. So P of X given T equals 1 is equal in distribution to P of X given T equals 0. I'd use a capital X here rather than a little x to indicate that we're talking about a conditional distribution. So on the left, it's the conditional distribution given treatment equals 1, and on the right, it's the conditional distribution given treatment equals 0. And covariate balance means that these two distributions are the same. And the variable x here doesn't need to be a scalar. It can be a vector of any size. Alright, we're talking about why randomization is magic, so we'll first show that randomization implies covariate balance before we show that covariate balance implies that association is causation. The key thing here is that because T is determined by a coin flip and not by anything else, right? It's not determined by any covariate, any variable in X. Because of that, T is independent of X. So because T is independent of X, we can write that the conditional distribution of covariance in the treatment group is the same as just the marginal P of X. And we can do the same for the control group. Then because these two conditional covariate distributions are both equal to a marginal, they're also equal to each other. And that's covariate balance. So we have that randomization implies covariate balance, and this is because randomization makes it so that T is independent of X. Now that we've shown that randomization implies covariate balance, we'll now show that covariate balance implies that association is causation. So in this slide, we'll start with covariate balance, and then we're going to show this. So we're going to start with P of y given do t, and then we're going to prove that that's equal to P of y given t. This is the way of saying association is causation in math. And because randomization balances all covariates, we'll let X be a sufficient adjustment set here. Then because X is a sufficient adjustment set, we can use the backdoor adjustment. Then if we multiply by P of t given X divided by P of t given X, we get this. So this is just multiplying by 1. And then notice that the numerator here is actually the joint distribution by the chain rule of probability. Then on the last slide, we got covariate balance in the top left here by saying that t is independent of X, but also covariate balance implies that t is independent of X. And we can use this independence to simplify the denominator here to get just P of t in the denominator. Then using Bayes' rule, we get this. And finally, we can marginalize out X to get P of y given t. So we've started with covariate balance and proved that it implies that association is causation, assuming that the covariates that we've balanced are a sufficient adjustment set. which is the case with randomization because randomization balances all covariates. Okay, so here's what we saw in this perspective of why randomization is magic. On the last slide, we saw that randomization implies covariate balance, and then on this slide, we saw that covariate balance implies that association is causation. So this covariate balance perspective gives us one way of seeing why randomization implies that association is causation. We'll now see two more perspectives on why randomization is magic, each of which will only take up one slide. So the next is exchangeability. To see why we have exchangeability when we have randomization, consider that we assign someone to the treatment group t equals 1 when the outcome of the coin toss is heads, and we assign them to treatment group t equals 0 if the outcome of the coin toss is tails. And the average outcome in the treatment group is y1 and the average outcome in the control group is y0. Now consider what would happen if we were to just exchange heads and tails here. So now the people who get tails are assigned to the treatment group and the people who get heads are assigned to the control group. Because we're just exchanging heads and tails here, the expected outcome in the treatment group and the expected outcome in the control group will not change. They're just going to stay exactly the same. And that's because we're using randomization. We're using the outcome of a coin toss to decide which treatment group people are assigned to. So if we just exchange heads and tails, the group compositions in the two groups stay the same and the average outcomes in the two groups stays the same. That's why randomization gives us exchangeability. And this will bring us to our first question. We just saw on the last slide that randomization gives us exchangeability. Now write down the formal definition of mean exchangeability, and then prove that this yields that association is causation. So with this slide and the last slide, we have that randomization makes it so that we have that association is causation because randomization implies exchangeability. The last perspective that we'll see on why randomized experiments are magic is that they make it so that there are no backdoor paths. So if this is the causal graph that's generating some observational data, X is a confounder, which means that we have confounding association that flows along the path from T to X to Y. But in randomized experiments, we use a random number that determines treatment. And importantly, it makes it so that that is the only thing that determines treatment. So now there's no edge from X to T, which means that there are no longer any backdoor paths. Even if there were some unobserved variable that you thought might have a backdoor path, when we randomize T, there's going to be no edge from that variable to T. So there will be no backdoor path through any unobserved variables either. And that concludes the final perspective on the magic of randomized experiments. Consider this graph that we just saw. What previous result that we've seen tells us that association is causation in this graph? Now that we've seen why randomized experiments are magic from a few different perspectives, we'll move on to more general identification beyond the backdoor adjustment for the rest of this lecture. And the first is the Frontdoor Adjustment. Let's quickly recall the backdoor adjustment. So if we're looking at P of y given t here, we have non-causal association flowing along these backdoor paths. But we can fix that by blocking those backdoor paths by just conditioning on W2 and C, for example. So we can get identification in this graph just using the backdoor adjustment. But what about this graph, where W is unobserved, so we can't condition on W here? We can't block that backdoor path. Can we still identify the causal effect of T on Y if this is the causal graph and we haven't observed W? It turns out that we can using the Frontdoor Adjustment. So in this graph, we have causal association flowing along the directed path, T to M to Y, And we have non-causal association, or confounding association, flowing along the backdoor path t to w to y. And the intuition for the frontdoor adjustment is that because we have this m here, and all of the causal association that we're interested in flows through m, if we just focus on m, then we can isolate the causal association. And we'll see specifically how we'll do that in this part of the lecture. The big picture is that we'll do this in 3 steps. The first step is to identify the causal effect of t on m. Then we want to identify the causal effect of m on y. And finally, we'll combine these two to identify the causal effect of t on y. We'll take this step by step. So the first step is to identify the causal effect of t on m. That means we want to take this quantity p of m given do t and somehow turn this into an expression that doesn't have do operators in it. Well, it turns out that in this graph, there are no backdoor paths from t to m. That's because y is a collider on the path t to w to y to m. So because the collider y blocks that backdoor path, we have that this is just equal to p of m given t. That's all there is to step 1. Now in step 2, we want to identify the causal effect of m on y. So the causal quantity of interest is p of y given do m. Here there is a backdoor path from m to y. The backdoor path is m to t to w to y. But fortunately, we can block that backdoor path by conditioning on t. So we can use t as a sufficient adjustment set and just use the backdoor adjustment here. In the last slide, we actually got identification via the backdoor adjustment, with the adjustment set being the empty set. So you can think of the first 2 steps of the front door adjustment as just 2 applications of the backdoor adjustment. And then in the final step, step 3, we just combine what we got in step 1 and step 2 to identify the causal effect of t on y. So the causal quantity of interest here is p of y given do t. To get this, we start with the causal association flowing from t to m that we got in step 1, and we chain this together with the causal association flowing from m to y that we got in step 2. And then because this first one here, p of m given do t, is a distribution over m, we have to sum over all the values that m can take on. So we have some value of t here that we're interested in measuring the causal effect of. And what we do is we look at the effect of t on m. So there's some specific value of m here that then we look at the effect of that m on y. And we're chaining those 2 together. And then because this distribution of m given do t, it's a distribution, we have to sum over all values that it could take on to sum out that randomness. And then we actually know what each of these quantities inside this sum is equal to when we get rid of the do operators from steps 1 and step 2. It's just this. We have a t prime on the inner sum here to distinguish it from this t, which matches this t here. So that's the only reason we have t prime here. And that's actually the front door adjustment. So the front door adjustment is that if we have that t, m, and y satisfy the front door criterion and we have positivity, then we have this identification equation here. And what is the front door criterion? A set of variables m satisfies the front door criterion relative to t and y if the following are true. 1, m completely mediates the effect of t on y. So in other words, all causal paths from t to y go through m. M is a full mediator of the effect of t on y. 2, there is no unblocked backdoor path from t to m. This was key in step 1. And 3, all backdoor paths from m to y are blocked by t. This was key in step 2. If you want to see a full proof of the front door adjustment using the truncated factorization, then check out section 6.1 in the course book. The question for this section is, What is the intuition for why the Frontdoor criterion gives us identifiability? We just saw the Frontdoor Adjustment, which helps us identify causal effects when we can't use the Backdoor Adjustment. And we'll now move on to Pearl's do calculus. So here's an important question. Can we identify the causal effect if neither the backdoor criterion nor the Frontdoor criterion is satisfied? The answer is yes, and do calculus tells us how. Using Pearl's do calculus, we'll be able to identify any causal quantity that is identifiable, keeping in mind that not all causal quantities are identifiable. Here is a general, non-counterfactual causal quantity that you could be interested in. P of y given do t, x, where here y, t, and x are arbitrary sets. They don't need to be scalars. So x could be many covariates, t could be multiple treatments, y could be multiple outcomes. Before we introduce the rules of do calculus, we have to show you a bit of notation. And we'll use this example graph G to illustrate this notation. The graph Gx with the bar underneath the x refers to G where all edges going out of x are removed. The mnemonic to help you remember this is that if you think of parents as above their children, then you're cutting all of the edges that are going out of x with this line below x. Then if we look at G again, so we can look at G with x with the line over it. In this graph, as you might have guessed, we cut the edges above x. So that's G sub x with the line over x. The mnemonic is the same here. We're just cutting the edges that are above x when you think of parents as being above their children. And then if we added on z with a line below it here, we would just be cutting the outgoing edges of z. With that notation introduced, we can now show you the rules of do calculus, starting with the first rule of do calculus. This first rule is about when we can remove z here from behind the conditioning bar. We can do that when y is deseparated from z in the graph where the incoming edges to t are removed because we've done t here. And we're conditioning on w. So it's deseparated given w and t. So that's rule 1. That tells us when we can remove z from behind the conditioning bar. And my question for you is, what concept does this remind you of? What if we were to remove these do t's and change the graph to just g? Then we have this special case of rule 1 where t is the empty set. This is just regular deseparation, and this is what it implies. It implies conditional independence in the distribution, given the Markov assumption. So rule 1 is just a generalization of deseparation to interventional distributions. If you get the intuition for why deseparation implies conditional independence, then you get the intuition for rule 1 of do calculus. Let's now move on to the second rule of do calculus. So here is the second rule. And I have the same question for you again here. What concept that we've seen previously does this remind you of? If we apply the same trick as we did on the last slide of taking the treatment to be the empty set, then we get this special case of rule 2. Hopefully, if you couldn't answer the question before, hopefully you can now. So what concept that we've already seen is this line here? This is the framing of the backdoor adjustment in terms of deseparation that we saw last week. So rule 2 of do calculus is a generalization of the backdoor adjustment / backdoor criterion, where we've added this do t here. The final rule, rule 3, is the trickiest rule, so we'll spend a bit more time on this one. This is rule 3. where z of w denotes the set of nodes of z that aren't ancestors of any node of w in the manipulated graph. Alright, so to try to understand the intuition for this rule, we're going to do the same thing as always. Let's remove these interventions on t, so consider the special case where t is the empty set. That gives us this, so if y is d-separated from z by w in the graph where we remove incoming edges to zw, then we can just remove the intervention on z. So here p of y given do z comma w is the same as p of y given w. Okay, so to think about how we might get this, let's consider the association that's flowing to y. So in this graph, there's association flowing from z to y only along directed paths. That's because the graph associated with this quantity, there are no incoming edges to z. So we only need to worry about causal association flowing from z to y along directed paths. So we can remove the do z to get this quantity if there is no causal association flowing from z to y. If there are no unblocked causal paths from z to y. So under what conditions would there be no causal association flowing from z to y? You might think it would be when y is d-separated from z by w in the graph where we've removed incoming edges to z. Because when we remove incoming edges to z, the only association between z and y is causal association. So if they're d-separated, then there is no causal association. You might have this equality. So why do we have this weird zw here, where zw denotes the not quite z. It denotes the set of nodes of z that aren't ancestors of any node of w in the manipulated graph where we removed edges in going to t. So what's going on here? Why do we have z of w instead of z? First, if you don't understand the intuition for why you might expect z here, then go ahead and pause and think a bit about that to convince yourself why I'm saying it might make sense for z to be there. Now, to see why we have z of w instead of z for this rule, we're going to have to consider colliders. So colliders are the key here. To see that, consider this graph. Here I'm using zw to refer to a node in z that is an ancestor of a node in w. And I have w conditioned on here, right? So w is behind the conditioning bar. And because w is conditioned on, and because it's a descendant of this collider here, there is a path of association. So there's association flowing from a to zw to b to y. So y is the key variable that we care about here. We want to know under what conditions do z does not affect y at all, right? So when can we remove do z from behind the conditioning bar and not affect the distribution of y? And in this graph, we just established that y will have association flowing into it all the way from a to zw to b to y. And if we were to just have d-separation between y and z in the graph where all the edges are deleted from every node in z, then we would be killing that path, right? Because zw is a node in z. So we really could have that the distribution of y changes when I do z if I only have d-separation between y and z in this graph. That's why we need to consider the nodes in z that are not ancestors of the conditioned on w, because then they won't be, potential colliders. And then if we don't condition on these kinds of nodes, we can keep this path intact. That's why this criterion is only with the nodes in Z that are not ancestors of W, and it's not this criterion here. So this is the more general version of Rule 3 when we add in this do T here. And that's the intuition for why Rule 3 of do calculus is true. This is a bit of a tricky one, so you might want to pause here and think more about this to kind of help cement that intuition. And those are the rules of do calculus. We use these rules to identify causal quantities. In other words, we take some causal estimand and remove do operators from it, turning it into a statistical estimand. As an example of using these rules, we give a proof of the Frontdoor Adjustment using the rules of do calculus in section 6.2.1 of the course book. We gave a proof of the same result using the truncated factorization in section 6.1, so you can compare the proofs using the rules of do calculus versus using the truncated factorization. So that's all great, but recall that we started this section noting that the backdoor adjustment and the frontdoor adjustment were ways to identify causal effects, but the backdoor criterion and the frontdoor criterion are not necessary criterions, right? So even though they give us identifiability, if they're not satisfied, that doesn't mean that we don't have identifiability. And maybe it's the same with the rules of do calculus. Maybe there are some causal estimands that are identifiable, but that we can't identify using the rules of do calculus. Well, it turns out that that's not the case. Fortunately, do calculus is complete. In other words, if a causal estimand can be identified, if it's identifiable, then we'll be able to do it using some sequence of applications of the rules of do calculus. You can look into these papers for more information and the proofs on that. And these proofs are constructive, which importantly means that they admit polynomial time algorithms for identification. So we can automate identification. With that, we can conclude the section on do calculus and move to this question. What concepts are the first and second rules of do calculus generalizations of? You should be able to use your answer to this question to easily remember the first and second rules of do calculus and why they're true. While the rules of do calculus are great because they're complete, just those rules doesn't make it easy to know whether some causal quantity is identifiable from just looking at the graph, like we could do with the backdoor criterion and the frontdoor criterion. In this section, we'll look a bit further on how to determine identifiability from just looking at the graph. To motivate this, let's start with a question. So consider this graph here where W1 and W2 are unobserved. In this graph, is the backdoor criterion satisfied? How about the frontdoor criterion? Is the frontdoor criterion satisfied? The first more general criterion that we'll consider is what we call the unconfounded children criterion. So consider a single treatment variable here. This criterion is satisfied if it is possible to block all backdoor paths from the treatment variable t to all of its children that are ancestors of y with a single conditioning set. So this is a sufficient condition for identifiability when there's a single treatment variable. And this criterion generalizes the backdoor and frontdoor criterions. Let's visualize the flow of association in the graph that we saw in the question on the last slide. This path from t to w1 to y that can't be blocked because w1 is not observed is why we can't use the backdoor criterion. And this path from m1 to w2 to y where w2 is not observed is why we can't use the frontdoor criterion. The intuition for why the unconfounded children criterion gives us identifiability is that we can isolate the causal association flowing out of T by focusing on these edges from T to its children. And we can isolate this causal association if the relationship of T and its children that are ancestors of treatment is unconfounded. If it's possible to block all of the backdoor path from T to all of its children using just a single conditioning set. This focusing on the causal association flowing out of T and into its children that are ancestors of Y allows us to remove the non-causal association. In other words, it gives us identifiability. If you see the similarities between this intuition and the intuition for the Frontdoor criterion, then great. If not, you might want to spend a bit of time drawing the connections between this intuition and the intuition for the Frontdoor criterion, giving us identifiability. But remember that the Frontdoor criterion is not satisfied in this graph, so this criterion is a bit more general than the Frontdoor criterion, which will mean that the intuition is a bit different, even if there are similarities. The unconfounded children criterion is a sufficient criterion for identifiability, but it isn't necessary. As an example of a necessary condition for identifiability, consider this one. For each backdoor path from T to any child M of T that is an ancestor of Y, it is possible to block that path. The intuition is that any causal association flowing from T to Y must flow through its children, and it's only going to flow through the children that are ancestors of Y. So to be able to focus on or isolate all of that causal association for any one of those backdoor paths that produce confounding association, we must be able to block that path. So why is this not also a sufficient condition for identifiability? To see why, consider this graph. Here, Y is the only child of T, and we'll consider it an ancestor of itself. And there are two backdoor paths from T to Y. The first is T to W1 to W2 to W3 to Y. Luckily, this path is blocked by the collider W2, so we can block this path by conditioning on the empty set. And the other backdoor path is T to W2 to Y. And we can block this path by conditioning on W2. So there are two backdoor paths, and we can block both of them. But we can't block them both with a single conditioning set, because if we condition on W2 to block the backdoor path T to W2 to Y, then we unblock the other backdoor path, because W2 is a collider. So this condition isn't sufficient for identifiability, because even though we need to be able to individually block any of the backdoor paths from T to its children that are ancestors of Y, that doesn't mean that we'll be able to block all of these backdoor paths with a single conditioning set, which is what was required in the unconfounded children criterion on the previous slide. Okay, so we've seen a condition that is sufficient but not necessary on the previous slide, and now on this slide we saw a condition that is necessary but not sufficient. What about a graphical condition that is necessary and sufficient? So recall that we already saw that being able to take some causal estimand and turn it into a statistical estimand using the rules of due calculus is a necessary and sufficient condition for identifiability. But this isn't graphical, so it's not as appealing. For a graphical criterion, see these papers. The first one is the main paper, and then in the second paper they extend it to conditional interventional distributions. The necessary and sufficient graphical criterion is known as the hedge criterion. We won't actually get into it in this course because this criterion requires defining other more complex objects like seed trees and other leafy objects. And we'll conclude this section with a question. So consider this graph here. Is the unconfounded children criterion satisfied here? If I change the graph to this one, how about here? Is the unconfounded children criterion satisfied in this graph? And in this graph, can we get identifiability via any simpler criterion that we've seen before this section? With that, we'll conclude this lecture. If you want to get notifications when I upload future content, then hit the subscribe button and bell below. And don't forget to leave any questions or comments in the YouTube comments below.